CI, and we've been talking about it for a long time, but now that Eric Bray implemented compound models in modeling, it became possible to actually do the work. And I'll briefly mention the goals for the project, and then I'll do two demo examples. So one of the major goals is to provide WCS toolkit, which is much more flexible than what's possible with the FITS WCS standard. And when we talk about WCS, we mean all the transformations from the detector to a standard coordinate system. This means we include all the distortions or any other detector anomalies that need to be corrected. This toolkit should be able to combine transforms in an efficient way such that resampling is done as little as possible, possibly once at the end. The pipeline of transformations is a combined transform, but the simple transforms we should be able to manipulate the simple transforms as well as we should be able to manipulate the pipeline as a whole, which means we should be able to insert new transforms or delete existing transforms. We want to be able to handle cases with discontinuous WCS models like the IFU data. And we want to be able to handle quantities as input coordinates. And by that, I'll give an example of an IFU. Another major goal is to be easy to extend this toolkit. It's based on AstroPy modeling, which is a pure Python package. So it's already easy to write new models in the framework of AstroPy modeling. But it also is possible to use as a transform any Python executable or callable object. It uses AstroPy coordinates, wraps the low-level coordinate frames as frames in GWCS, and just adds a few more parameters to them. And this makes it easy to write new coordinate frames. A little bit more about combined models. They exist in AstroPy modeling since version 1.0. And I'll just briefly go over what their capabilities are. Here in this example, I simply import a few models, shift scale and a polynomial. It is possible to do binary arithmetic operations with simple models, just like with numbers. In this way. Another way to combine them is to chain simple models. This is the operator we use for chaining. The output of one model is passed as an input to the next model in this case, and of course the number of output coordinates of the first model should match the number of input coordinates for the next one. And finally, we allow model concatenation, which is we can combine coordinate transforms on independent coordinates to create one compound transform. In this example, I have two shift models. The first one shifts the first input, and then a shift in the second input, for example, x and y. And I can combine them and execute them at once. There are a couple of classes for access management in AstroPy modeling, mapping and identity. In this example, let's say my input is x and y, and poly x is a 2D polynomial correction in x, which takes x and y as inputs, and poly y corrects y, but also takes x and y. I join poly x and poly y to create a compound model called poly here. This model now needs 4 inputs, x, y, x, y. And I use the mapping model to create those 4 inputs. The mapping model takes a tuple as an input, which is represent indices in the in the original input. So as you can see, the number of inputs for the mapping model is 2, and the number of outputs is 4. Then I can chain the mapping model with the combined poly model to have one transform. Mapping can be used also to drop axes. In this example, I have 3 inputs, but I'm only taking the first and the last one and dropping the middle one. And finally, identity. This is a class which simply passes the input unchanged. It takes one integer as input, and the integer represents the number of inputs which should be passed unchanged. It is usually used with other modules, joining with other modules. All right, so now on to the demo. I have 2 examples in this demo, one imaging example and one IFU. And here I just simply import a few things I will need from modeling, and yeah, mostly modeling. So the main import is from GWCS import WCS. I have another module here called tools, which is specific for this tutorial. It only has a few functions which help me read models, so I can pass them to the WCS object. And in its simplest form, it takes an output frame and a forward transform. So I read a forward transform here, which is a transform from pixel to sky, and I'm reading it from an ASCII file. The ASCII, Mike talked about the ASCII format a couple of days ago. It has another parameter called input frame, which is set by default to detector. And the pipeline itself is represented as a list of steps from one coordinate frame to another, and then the transformation between them. The last transformation is a none, always, so that signifies the end of the pipeline. The WCS object is, we simply call it, it's a callable object. We call it to perform the transformations, the forward transformation. It produces numbers, floats. The result is floats. And the invert operation, if it exists in analytical form, is done by the invert method. If it doesn't exist, an iterative inverse can be assigned to the WCS. However, this was the simplest form to call the WCS. We actually have a little bit more control over how we create this. We can, instead of passing strings as coordinate frames, we can actually pass real coordinate frame objects, which gives us a bit more flexibility. In this example, I'm creating a detector frame, a focal plane frame, and a celestial frame, which is ICRS frame. And I am also reading 2 models from files, distortion model and focal to sky transformation. And then I create the pipeline before I actually pass it to to the WCS object as a list of tuples. So the WCS object is created in the same way, and this is its representation. It has an attribute called available frames, which is simply a dictionary which maps the name of the frame with the real WCS object, coordinate frame object, if it exists. And executing it here. The output frame object has a world coordinates method, which, if we pass the output of the WCS, it creates a world coordinate object. In the case of imaging and celestial frames, it creates a sky coordinate object which then can use the AstroPy coordinates framework to convert to any other standard coordinate system. Okay, so there's a method on the WCS object called getTransform. It takes two frames and returns the transformation between them. In this example, getTransform returns the distortion or the transformation between detector and focal plane. Now let's suppose that I need to do some additional correction and add additional transformation to the distortion, which is a shift in X and a shift in Y. I can create the transform and use the insert transform method to insert this transform in the pipeline. Frame here is the focal plane because I want to insert the transformation immediately before it. And then there's a Boolean parameter which says whether it should be before or after the frame. After retrieving the transformation again, I can see that it's in the pipeline now. All right, this is the imaging example. I will briefly do an IFU example. There's a model in GWCS called selector model or region selector model. It basically maps slices of the IFU with transforms, and also, but to do that, it needs a mapping between the slice and the detector. It basically needs a mask. Here I'm creating the mask, and I'm using the MIRI instrument as an example. It has 28 slices, 2 channels. This is the mask on the detector. It basically says each pixel belongs to some slice number. The MIRI model's function simply creates a dictionary which maps the slice number with a transform, and I can pass the MIRI models as a selector parameter and the detector mask as a selector mask to create the region selector model. I'll skip this. This just creates coordinate systems and eventually creates the IFU WCS object for the entire IFU. Running the IFU WCS object creates 3 outputs in this case: alpha, beta, which are spatial outputs, and lambda, which is the spectral output. And finally, these are the plots for the 3 planes, alpha, beta, and lambda. And this last line there just shows that I can actually retrieve the transformation for a particular slice. And just to end up, I think my time is up, but I just want to add that this is still a work in progress. This is the GitHub repository and the documentation. What needs to be done is we need to finish how we serialize the entire WCS to a file using the ASCII format and write tools around the basic functionality. We need to integrate this with the regions and also develop fully the coordinate systems. There's like a start for spectral coordinate systems and spectral objects, coordinate objects in GWCS, but maybe now is the time to think whether we want to include these in coordinates. So that's it.
Questions?
Very nice. I think, this is something that we've been waiting for a while, and I think it turned out really, really nice. A couple of questions. Well, one comment for the spectral coordinate system. So one of the things that I'm already talking to Michael Gertboom about, and also to you, is getting some of the stuff from specutils into your making GWCS, because I think that should be very trivial. The other question I have, a design choice, is you basically have a WCS object, I mean, just create your code, and you inherit this from object rather than from a model. So you have this additional sort of layer. So I was wondering why the WCS object is not directly a model.
Because it's really a pipeline of models, but it also has to know about coordinate frames. It is important to include intermediate coordinate frames in the WCS pipeline and be able to retrieve transforms that are between them and insert other transforms. This will make it will make it easier to also convert coordinates from, for example, from detector to some other frame that is intermediate frame that is important for an instrument, and do things with these coordinates there. So that's the reason.
Suggesting making this a model, but inheriting it from model, because the modeling compound model is already a pipeline in that sense. It does exactly that. So I don't know. Maybe there's good reasons.
Yeah, I see your point. It's a possibility, but actually it's way more difficult to write the code that way. I think.
Thank you.
And just to add to that, models are intended to be sort of mathematically pure, and these are adding all this metadata about frames and additional meaning and context that isn't perfect fit.
Yes.
So I suppose now we have the modeling in the GWCS and almost the ASPF. Maybe the part of the remaining thing now is actually have some library sampling stuff to go with it. I think we kind of assume that somewhat done.
Well, the principle to reproject ought to be able to take WCS objects.
I think this right. This falls into creating tools around the basic functionality. Yeah, it would be nice to have.
Will have to throw support for this somewhere.
Right.
Which I'm not committing to.
It's actually a bit of a pending problem, I think, we rejected. We have MBA, general review sampling. It's always been a bit of a mess internally, no one can really maintain it, but step answers, but I think they want to be working. I think maybe it's occasionally have some students who work on it.
Yeah.
We don't have a project for it. It would be very nice to be able to do that. It's probably something that does a lot of work.
Another area that we can make progress on now is if we pull this into the NV data object.
Yes.
A lot of functionality in the NV data object is sort of waiting, what are we going to do about WCS in a more general way?
Yeah, it would be good to reach consensus to be able to replace that
Yeah.
attribute.
I think there's nothing stopping us. Like WCS currently in any data is not having a certain type or expecting a certain type. Well, I always assumed in my mind that GWCS would just be attached to any data. So I think there's actually nothing stopping us from using this for science, almost.
Yeah.
Any other questions? Anyone? No? Okay, well, let's thank Nadia.